All right. So we're going to take a quick look now in this video how to actually do some performance profiling on your application live in a Kubernetes cluster. I'm Ray Ko. I'm one of the Azure Global Black Belts covering cloud native computing and digital app innovation. With me today, I've got my good friend and teammate, Diego. Diego, you want to introduce yourself?
Hey, I'm Diego Casari, also same team as Ray, App Innovation, where today we'll be looking into some different approaches, I suppose, on how troubleshoot or do CPU performance analysis on workloads on Kubernetes.
Yeah. So it just like as another gist of what we're going to go through. This is one method that you can kind of use to check out or profile an existing application running your cluster. You might have a scenario where, oh, this thing is not performing the way that we expected to. We're not sure what's going on. Sometimes we've seen customers say like, I've written this, pristine, perfect code. There's nothing wrong with it. What could be messing it up? It's slow to respond, or it's chewing up a lot of CPU. How can we figure out what's going on either in a live scenario, or maybe we run it in a dev or test environment to try to figure out what's actually going on in sort of our call stack in a container live in a Kubernetes cluster.
And we're going to be doing this live as all the cooking shows out there.
Yeah, live-ish. Wherever you mess up or we have too many ahs and ums, we'll just kind of edit that out. But yeah, yeah.
So, a couple of things, Ray. I think before we kind of go anywhere, I'll go around just what kind of tools we have to set up. But I want to give a good shout out for Marcel Dampers. We'll have a link for his YouTube video. Um, his initial work led us where we are today. So I definitely want to recognize that and make sure that folks are checking his work.
Great.
So what do we have here, Ray? We have an application that's called bad deployment here. Again, that's coming from Marcel. So we're going to profile that. I've made some modifications on the tooling that we have. I am using VS Code just to illustrate. You can use some other tools if you wish to do so. That's not a problem. But the primary util that we have, it's called Fireball, and it is available today on our app innovation GitHub repo. Again, we'll have a link for that in the description. And in a nutshell, what the scenario that we have here, it's a Ray, I'm gonna say it's a common scenario that you and I have seen many times where we are helping our customers um, understanding their performance or how their application is actually behaving. The difficult part when you have a containerized application is just where to look, honestly, because it could be in too many places. If you don't know whether or not it's just CPU bound or network or storage or whatnot, it becomes a challenge, right? I think you and I have seen this over and over again.
Hmm. So
So
basically, like we have a poorly performing application. Where's it going wrong? Is it just using like a sort of some kind of blocking process that's eating a lot of cycles? It's chewing up an entire thread. It's not doing async sync properly. Maybe we have a bottleneck on disk write, right? Like maybe it's a network attached storage device, and we got some latency issues there. Maybe we've got some networking issues. So this will kind of help us track down where that could be kind of going off the rails.
those are good points. I mean, let's start by kind of like looking at this application. We do have the deployment here. And again, in certain situations, when we're looking into a running application, we typically go and see, let me see your deployment, let me see your pods. Um, there's nothing that stands out by just looking at that. So let's look at the pod in here. We
So
probably
just
don't
just
have.
uh, as like this is not like files on your local machine. This VS Code, the Kubernetes plugin, basically you're already connected and authenticated against the Kubernetes cluster. And on the left hand side there, you're able to traverse all the uh, resources inside Kubernetes that you would normally do in like say kubectl. But in this case,
Yes,
it's just like the UI click click click.
yeah, that's right.
Yeah.
So let me just highlight. So I do have the extension for Kubernetes, and I am logged into your point Ray in the cluster already. And
Mhm.
then at this point, we're looking into two things. We're looking into the deployments in here,
Yeah.
and then also the pods. I am using VS Code here just because it's a lot easier to showcase what we're trying to do.
Mhm.
But again, you could do everything from just kubectl. If that's all you have, that's all you have. You go with that. That should work.
Yeah.
For this demonstration, yeah, the moment I click into deployment, or pods, that YAML that I get back on my screen,
Yeah.
this one, it's actually coming from the cluster, right? I'm just retrieving that and I'm using VS Code to see it.
Yeah. Very cool.
But initially, when you're faced with a problem like this one, uh, I think we would probably agree that you want to go with something like kubectl,
I forgot the K.
kubectl. Um, you can do a get pod in here, which will give you the same information there. But I think a top node potentially.
Yeah.
So one of our nodes is running about 60% CPU. That's probably where the workload is. I haven't checked that out yet, so we're gonna take a look at that. And I can also do um, a top pod, right, to see that. And we also get back um, the bad deployment pod, and it's really the one that's chewing up a lot of CPU. We can, you know,
So when you say bad deployment pod, it's just that's what you named it. We don't know
that's what I
yet.
name
Like
it. We could
as part
name,
of our yeah, as part of our
yeah.
detective work, we don't actually know this is the bad pod yet, but we're
We're
making
we're
assumptions
making
during
life a
this
little
cooking
easier
show.
here.
Yeah.
So the name of the deployment has bad in front of it.
Yeah.
Um, but you could have something else.
Yeah.
In
It could be
real
named
life,
something
you're not
else.
gonna have
Yeah.
bad. You're gonna have just something else altogether.
Yeah.
So here's the interesting thing though. If we do that, and again, I can just go back through VS Code, and then I can look around to see where exactly is this so-called bad pod, which right now we don't know how bad is bad. So we're kind of trying to understand that. I could try to make sense out of that in a describe, but but just to confirm, because we know that one of these nodes, this one here, it's the user node pool. So also a little bit of a hint here, but you might have more node pools, or this might be running in a different node pool. So we're just gonna do a get pod, and then I'm gonna pass a flag called wide, so dash o wide,
Yep.
and that should tell me here more information about the running pod, right? So now I can say for sure that this here, um, it's actually the one that I'm looking for, right? That's that pod is running on this specific node, and I can see the spike in CPU when I'm doing kubectl top node. So I think that's probably an initial like investigation that folks will want to do, which is, if you don't have another type of instrumentation here, then we're gonna cover this in another video later on. But you might potentially have something like Grafana and Prometheus that would help you see CP over time, or Azure Monitor, or other tools. But this is probably the one that is available from the get-go, right?
Just some easy diagnostic or like easy like detective work. You can kind of align those things, right? Like top thing that's chewing up the most resources, and then try to like drill down and kind of match it up, right? Like top pod tells me that's going to be the resource hog, and then I can kind of point to those indicators that okay, yeah, these are kind of two pieces of data that are converging together to say this is likely
For
our
sure.
bad candidate. Yeah.
Yeah. And if I rerun top pod, but if I um, have all the namespaces, so I'm actually opening it up so I can see all the namespaces now. This is probably even more interesting because you can tell that that is this application that is chewing up pretty much one CPU, and then you can see all of the others that we have, and they're not behaving like that. So
Mhm.
that's another way, that's another view you can do across the entire system, and all the node pools and all the namespaces, and get an idea, right?
Right.
So Ray, I mean, if naming it bad deployment wasn't gonna help in our detective work, I think the CPU there might be the one thing that we can use.
Yeah. If only we could just name them in advance and like a crystal ball, we know for sure that's what's causing us trouble, right?
Yeah. Um, so let's go with that. Now, what do we have? Again, out of the various tools, so if we're investigating this and I want to see, I know that it's a CPU bound issue. I can see it. It's really high.
Mm.
At least that's my initial suspicion here. It could be like looping on CPU waiting for something else too. But as it stands right now, we're going to try to take a look at how the application itself is behaving on the CPU. Um, so for this, we're gonna go back and use some of the work that Marcel did himself, which is pretty much based on Brandon Gregg's flame graph.
Yep.
Now we're gonna see the flame graphs here. in a moment. I'm gonna run the application. And once we get the flame graphs, we'll go analyze and try to sense out of that. And just remember, we don't have the source code for this, right? So this could be also those legacy applications.
Yep.
They're running in the cluster that for some reason are misbehaving, and we're trying to understand what is happening, right? What kind
Yep.
of introspection we get.
Yeah. So the common scenario, right? Like you mentioned one scenario, legacy application, we don't have the code anymore, or no one understands it, even if we had access to it. Could be some kind of like commercial off the shelf application, right? We bought it from a vendor. We don't actually have access to their source code either. And even if we like, we can't dig into the code anyways if we wanted to because it could violate some licenses, whatever that scenario may be. Basically, it's a black box, but we want to get some information out to say, hey, this is likely our culprit, and at least if we have license support or if we do have a lifeline to whoever can actually update that code, that we can at least give them some kind of indication as to where we see this kind of having gone off the rails.
Yep, that's
Yeah,
absolutely that's what it is. Now, for this, so for this example here, we're gonna use a tool, a utility called Fireball. I'm just gonna execute it here. Again, it is just it's a bash script, so you could potentially do this in a headless environment. So you don't have to have all the setup that I have here. Potentially, you have to SSH to a jump host or a bastion host, and you're gonna execute these commands from there, and then only from that point you're gonna retrieve the information. You could do that because we're not relying on having anything locally on my machine for that. So I
yeah.
think that's the
So
benefit.
So just a step back, like all this tooling you could just have installed onto a separate machine, but what you're running here is a script that will basically get all the tooling that you would normally do manually by hand, be able to profile that or like, figure out what it actually needs, build the tooling itself, and then deploy it into the cluster, right?
Right.
Yeah. Another thing that you didn't mention is this Fireball tool. You made this. Yes?
I made this,
Yeah.
yes. So
Okay.
again, the initial work, it was things that I saw Marcel doing, and
Yep.
then out of that, I wrote from scratch what we have today. Still references a couple of files there, but yeah, I wrote this tool so that it would help us out troubleshooting this. Now,
And we'll put a link to that in also the description to your repo.
yep, and we're
Yeah.
pointing this to our app dev GBB repo,
Yeah.
so we do have that in there.
Yeah, our team's GitHub repo that we put some demos and other tools
And
in there.
honestly, Ray, like honestly, because of what we do day to day here, I think most of the folks in our team do what I'm showing you here. This is pretty much a common day in GBB life where we are prompted with these types of challenges with customers.
Mhm.
We can absolutely do this manually, but we automate. We tend to automate. We tend to make tools, and we use a lot of our own tools here. So that's, I think this is a good example of just how we're doing stuff on our side. It
Yeah,
kind of give folks a glimpse of how it is.
cool, very cool.
So what do we have? And I'm not going to explain how exactly this works. We'll go over the detail, but I want to show you how potentially easy this could be now. So we need to know the name of the pod, which we do, which is this bad deployment here, right?
Yeah.
So I need
So
that.
all the steps we did before to try to figure out, okay, who's the likely culprit, right? Like in our case, it's a cooking show. Of course, we know which one it is. It's called bad deploy, but we're trying to figure that out. So we found it out before, and now we're gonna pass that pod name in as a parameter in order to target it and then try to actually profile it.
Profile it.
Yeah.
So the only flag we need, Ray, is the name of the pod. And to your point, we kind of did a little bit of a Sherlock Holmes work where we found this pod. We found some because we didn't realize that when it says bad deployment, potentially that was just a joke. So, but we did confirm that the CPU is high. Let's use a tool now. We're calling Fireball to attach a profiler, an eBPF profiler. So I'll go that in a second, and then retrieve CPU metrics, um, and then dump that into our local machine as a flame graph, which is a lot easier to for us to make sense than to look at raw perf metrics in Linux. So that's like in a nutshell what we're gonna try to do here.
Very cool. So we're running this. We're going to create the container based on some information we profile on the pod ahead of time. Create the container, have it deployed in the Kubernetes cluster. and then it's just going to run on that remote node in the cluster, grab all the information, generate basically this reporting file, which is an SVG, and then it'll also automatically download it or copy it onto my local system so that I can actually view and introspect it.
That's right. So that as
Yeah,
like if you think about like an SRE
yeah,
engineer who is doing this day in day out, it can be pretty time consuming to do everything by hand. So
yeah,
the more automation we can provide, I think it would save folks a lot of time trying to do and just piece this stuff together.
yeah.
So let's do this. We know the pod. This is the one. I'm just gonna copy its name and I'm gonna paste that in here. Again, I'm just passing this as this single flag. We're gonna run it. We'll see what's happening. So as we run, there are a few things happening here, and I'm gonna refresh so folks can see that there is a new pod called eBPF Profiler that is running. What we get, behind the scenes is that as I execute against that specific pod, we are looking to see where the pod is running and what node, which we kind of know too because we did some commands by hand with kubectl get node and also get pod dash o wide where we saw the name of the node. And I'm doing the same here. So we have the running pod. We know the node, right? So that's a match because we need to execute a lot of these commands in a privilege mode inside of that node. So if we take a step back, Kubernetes is orchestrating running um, containers, right? That's essentially what it is. So in a single specific virtual machine or a node in Kubernetes language, we have a a container running. So as we executed there, we're running some commands to do some extra inspection on its behavior. And that's what this is doing. So pod maps out to a node. We go into that node with this eBPF profiler. We execute some commands to get its CPU performance, and we'll go over what kind of commands those are. We generate essentially Linux perf metrics. Those are coming from the kernel. And then out of that, we make sense of that information, which honestly, it can be, I'm just doing this for 30 seconds, but it can be overwhelming, Ray. I mean, if you look at the raw perf metrics, um, it's kind of difficult to make sense out of it initially. But if you use flame graphs, which is what Brandon Gregg developed, it's a visual utility. So it makes life a lot easier for you as like an engineer to inspect that, if that makes sense. And then at the end, we remove that profiler. So if I
Yeah,
refresh, this
before
should be gone.
before before you move on to that part, so just so that I'm processing it because I'm a little slower than you are. We've done our some of this investigative work on this bad deployment, right? This pod that's running. It's running as the regular privileges that we would give it, right? On a given node, and we have an idea of what node it's going. When you run Fireball, we pass in that pod name, so then the command or the script that you created takes a look at that pod, figures out what node that pod is running on, then deploys your eBPF tool, and you're going to describe how that actually gets created. But it'll run that second pod that runs this eBPF container, this workload that you have, on the same node. The difference between the two of them is that this eBPF tool now has as root privileges on the underlying host. So the worker node, the VM that you were mentioning before, and it's tying itself as closely or as directly to the Linux kernel on the host as possible in order to profile that bad deployment pod that's in the environment right now.
Yep, yep. That's a good explanation there too. And I'll show that here in a second.
Yep.
But one thing you did mention is we are using a specific version. You can see here that there is a specific Docker image that I've generated, and that's essentially based on the Linux kernel headers for Azure for this specific node. We need those because we need the symbols to make sense out of what we're doing here. Otherwise, you would see essentially a flame graph with a bunch of unknowns because Perf wasn't able to really make sense of what was running. So we kind of have to really go as low as we can um, to get that information out of the kernel and then populate it through perf so that we can make sense out of what we're seeing.
Right. So these are like real low level, like Linux kernel, like even like C headers for some of these things that are running on that particular version of the kernel. And more importantly, the what this script that you've created right now is tuned to Azure. So it's aware of like a certain handful of like Azure node kernel versions for Kubernetes. So depending where you're running this, like this could be readapted to, your Kubernetes environment, on your desktop at home. But do keep in mind that like your script out of the box is tuned to Azure kernel versions. So if I were to try to do this on my like a machine behind me, I have to
Yep.
basically check the kernel version of that uh, actual physical box or the VM that's running Kubernetes to make sure that it matches up so that the visualization I get at the end of this cooking show, it's not just throwing me things like, underscore unknown or things that I can't make heads or tails of. I can't point to something, right?
No, that's a good point. And we'll share right now there is specific to Azure, but I'm gonna share a couple of extra Docker files that I have where you can see here like the Linux headers and the Azure specific headers. We we import them again because we need them, and we also need the BPFCC tools, right? Those are fundamentally what you need out of this whole thing. Um, One other thing that you mentioned here that I want to call it out, absolutely go, fork what we have here, modify it to your own purpose.
Yeah.
I think we would love to hear how we can also help. I mean, we were helped out by Marcel. I would love to see how people can use whatever we have here um, to solve their own problem. I want to call out two things. One, absolutely, you're gonna have to change this, which I'm doing on build time. So you will see an example in our repo how you can actually use it. The second thing is that we are using CRI CTL for this. We're not just doing Docker anymore for the runtime here. So I have a specific version. In your case, Ray, you need to make sure that if you are using Docker, that you change this here because you need that utility to run, and then also the version, right? It needs to match the version that is supported for you. So I think that those are the two things you need to take care.
Yeah. So there's no expectation. Like if I were to just take your clone your script and run it on my environment for any Kubernetes deployment, there's no guarantee it's going to run because there's missing these couple of components here in order to
For sure.
get things
Yeah.
going. Yep.
Yeah, so you need to match the version of the Linux kernel, and then also the utilities, the user land utilities here. In this case, here ICTL, to to do what you're going for.
And I guess
The
the sorry, one thing before you move on though, the reason why we're using CRI/CTL instead of Docker is because
Well, it's because of what we have in Azure today. We
yeah,
really don't have. Um, so you're not going to be able to just run Docker. So even I'll give you a separate example here. On my own local machine here, I don't, I have to go with Podman. That's what I have. So yet another version, right? If I want to interface back with the running container runtime, that's just what I'm using. Um, if we had this conversation again like a couple of years ago, we will be talking about just running Docker.
yeah,
I think that's
because
how.
on the actual nodes themselves in AKS today, we've basically migrated away from Moby and Docker. We're just using pure the container runtime,
That's right.
container D, right there in that environment. So that's why we have to use CRI/CTL as opposed to bring Docker in this script.
Yep. And
Yeah,
I'm not, I'm just trying to use exactly what we have, and you can inspect this too. But I'm using
yeah,
exactly what we have in the nodes themselves.
yeah,
So for Azure, this is really tailored for that experience, running this against AKS,
yeah.
right? That's what we have.
So in theory, like not to go on too much of a tangent on this, if we were running this in say something like OpenShift, right? Like this is an Arrow environment, then would I be switching out CRI/CTL with Podman in that case? Because that would be the equivalent in like a full like Red Hat OpenShift stack.
Yeah, for OpenShift, you definitely need to change the runtime. But the way it would work in OpenShift will be different just because of the um, of Core OS versus just Linux and some of the headers and stuff like that.
Yep.
But you can potentially, I haven't, that's probably a good test though. I haven't tested this, but you can potentially kind of apply the same mentality in how you would go about.
Yep.
In if you were to do that though, then I yes say yes, it will be Podman, and this would be the core changes for you. You wouldn't really change the script. You probably just change what I'm showing here on the screen,
Okay.
which is honestly like a really light um, image. I mean, we're not embedding a lot of tools to have this running.
Cool. All right. Thanks. Thanks for the attention. So
No, this is good. This is a good conversation. I think this is a good dialogue to have. Just in terms of what we actually do here, again, you've mentioned we point to a pod, we attach to a node, we try to make sense out of that. There's a scenario that if you have more than one container in a pod, I will pick up the first one that comes back from Kubernetes. So when you do a describe against a pod and you have multiple containers, that operation, I'll take the first one, but I'll tell the user, hey, I'm using the first one that I got back from Kubernetes, but you have more. You might have two running as well. You can specify that. So if you want to profile a specific container in a pod, you can, right? In terms of like profiling time, we're just gonna default to 30 seconds. Again, you can do more. Um, but there's potentially a benefit for going more. Let's say 60 seconds. I don't think you want to go anywhere above, like a minute and a half or 2 minutes. The amount of information here might be overwhelming. So I'd
Okay.
start like do 30 seconds. If that's not enough, go, maybe double that, go 60 seconds and see what you get out of it.
Okay.
Most of the time you should be okay. The image of the profiler, again, right now I'm using the ones that I've generated. you you can generate your own. So to your point, how do I take this, modify it to my own use and run with it? Here's an option. You can point that image name to whatever you want. I actually have all of these as like flags, so you can point your specific. Maybe you have like an ACR, like an Azure Container Registry, and this is all private. So you can change that in here. And then the other actions is we allow folks to actually get a copy of the perf data, the raw data, locally. Or if you want to try to open the SVG image at the end of the run, you can. Right now, I support macOS and Linux. On macOS, we're just going to try to open with open. Um, and then on Linux, we're going to try SDG open and then see whatever it's attached to that, and the OS will open. You can also override those values.
Okay. So whatever the default. So when you say the raw perf data, uh, that's the SVG file that it generates, right?
No, that's actually before becoming an SVG file. We actually have a perf data here. Then if we take a look at the actual pod itself, and to your point, it's a privileged container. So I want folks to know what's going on here. It's privileged. You can see all of that in the YAML. But to call out, it's privileged. We do mount a bunch of namespaces in the actual node itself.
Mhm.
Why do we do that? Because again, we need to make sense of all of these different symbols. We might need to have access to different PIDs, process IDs, and C groups. So we mount some of those. And then what we do is we we execute all of these profiling tools, and the core one is called profile dash BPFCC. Again, coming from Brendan Gregg, we sample it at a 99 hertz frequency there, which is optimal for what we're trying to do. And then we generate a flame graph. So the option that I give for anyone who would like to see the actual perf data is this here. As we generate that sampling with profile BPF, it spills out this raw perf data, which you can see over time what's happening. If you need to have, let's say, another tool ingesting that data, you can just pass as a flag, and then you have a copy of that.
So I can pipe the result of that perf file into another tool as I'm running it. And
Yeah,
you said earlier that perf file by default is not being downloaded onto your local machine, right? You have
that's
to
right.
actually
It's
you
not.
have to pass that into flag. Okay.
Yeah, I didn't turn that on because again, most of the times folks are interested in the flame graphs itself, not in perf. But
Yeah.
perf is there and it's available if we have to use it.
Yeah. And so we use perf, we generate the perf file, then via the perf file we generate an SVG, a vector file basically that allows us to visualize all the data that's in the perf, right? So
Yeah,
if we're not a machine, right, we want to visualize it in SVG. If we are a machine, we'd look at perf.
that's right. So
Yeah.
why don't we do this? I'm just gonna run this one more time here, and because we do have the file. The file is local here, so I'm just gonna try to do the extra flag that's called try opening. Then again, it will do all the things that we've just mentioned. It will attach the running pod. We'll go into the node. We'll execute all of this BPFCC commands, generate perf, generate an SVG flame graph, And the extra flag that I'm giving here, right, this dash O try opening, is really just to automate the whole process, which is get the file locally and then open in a browser for me or in an application that can actually look into SVG files.
So it's gonna download even if I don't pass this dash O try opening, flag, it's gonna download the SVG for me, but what this will do is it'll also once it's downloaded, it will also try to open using my default SVG viewer on my
Yep,
local
it's just
machine.
like a little
That's
like extra step to and which you just did
and
down
then
here, right? So
okay.
let me go full screen here. Might be easier to see it. Okay, so if we were looking into this, and I suppose you've never seen this in your life, um, can you
Or
make some
in my
sense out of
case,
that?
I've seen this more than once, and I still have trouble
And
making
it
heads and tails of it.
okay, so what do we have here? I mean, let's try to look at what we have and see if we can make some assumptions. Out of the 2,933 samples, so roughly 3,000 samples we had in 30 seconds, 100% of the time, give or take in here, was spent in this stay busy method and then coming from a class called busy. You don't have the source code. You and I don't have the source code for this.
Okay.
So if we were having a conversation with a customer and we look into this, I think the conclusion here that we can initially say is, hey, you have a method called stay busy, and pretty much your application is stuck into that. Why don't we look into that? Would that make sense? Is that a
Yeah.
conclusion that you can make out of this?
So what we're seeing here too, like another step back, and this is like the basic extent of what I know. So everything from the bottom of this you know this stack that we're seeing is everything from like the kernel all the way up to like an actual like method that we're actually calling in our application, right? So from this we can kind of um, understand that okay, the thing at the very bottom called .NET called this thing called unknown, all the way up to this stay busy method or function at the very top of this, right? So that now that we see that that's the thing at the very top, it's always getting called or it's running um, all the time, or basically out of all the 3,000 or 2,933 samples we had, so 3,000 samples, every single time we did a sample, 100% of the time, this thing is always as part of our performance snapshot, right? Like it's always there. This thing's always running. And so we can kind of infer from this that this thing is a thing that's running all the time and is likely the culprit, right?
Yep.
Yep.
No, yeah, I think you got it. The other thing that Brandon Gregg, and we'll link to some videos that where he explains a little bit more in detail about flame graphs. But one of the things you want to look when you're trying to optimize your application is this like plateaus. You see, like there's a gigantic plateau here, and then might not be easy to see in the video, but there is something else on the side here, and we'll
So
inspect this too.
yeah, on the very far right hand side, there's still smaller little things that are in the stack, but they're being called a much smaller percentage of the time, and then they're also kind of being like called from what I can kind of see from this picture
And you can
is
see here now.
yeah. So that stay busy thing, that's the method that function is calling these additional pieces, but it's like a very like less than 1% of the time,
Oh yeah, it was like zero, yeah, 017, 023, I think was the other one.
right?
Now, the interesting thing that the discussions you're gonna have out of this is, well, some of my tools like Visual Studio will have a stack call. Like, what's the fuzz about what you're showing me here?
Hmm.
What you typically don't get out of IDEs is that in an IDE you're gonna see how the application itself behaves, and you can definitely profile, and you should use that. The moment it reaches out of the application and it hits the kernel, you don't see it unless you instrument it to see it. You don't see it, and this is exactly what we're having here right
Okay.
now. I mean, all of this here, there's not a lot that we can actually. I mean, it's only like 0.007%, but it's not like we're gonna optimize a lot of this. This is going back to the Linux kernel and it's doing like spin locks and things like that. We're not gonna go, and do a lot of things about that, but we get visibility. And in another example that I have here, Ray, I'll show you where why this actually matters. Why it matters to actually look outside of not only my application stack, which again, 100% in a scenario like this, you should instrument your application. so app insights and other other approaches, coupled with how do I actually see this from outside now, right?
Cool. So, like you mentioned, right? Like App Insights, VS Code, if I'm developing locally, or have the ability to like attach to the debugger in the cluster or whatever my running environment is, it just shows me the call stack of the application itself. But what you're saying here in the flame graph, it shows me, uh, it doesn't show me the stack necessarily of my actual application code, but it does see all the related things that it, my code, in this case, my .NET app, calls out to the underlying Linux kernel to make additional calls, right? Because we're leveraging underlying libraries that are part of the actual like Linux in this case,
Yeah.
in that
And
scenario.
remember, like, it's also like running a containerized environment in Kubernetes in a public cloud. You have all of that.
Yeah.
How do I make sense of what's working here? Sometimes the initial folks are not aware of how this actually works because of the complexity on this level. I mean, what we're looking into here. So they will say, well, do I have the right SKU of a VM? Do I have to bump it up? Maybe something like this will tell you whether or not you should do that.
Right.
Is the application actually misbehaving? Because I, took it from one environment and I now shifted to run in a cloud. And many times those decisions, you need to have enough data to back you up and understand what it is. And
Hmm.
then something like this will show you both cases. Will show me the actual running stack, um, and of course, like if you're actually running this inside of something like Visual Studio, you'd have a lot more information than what I'm showing you here.
Sure.
But I
Yeah.
think this is still valid though.
Yeah. We mentioned application insights, but for those who aren't familiar with it, like that's our like metrics and logging platform, right? So you might have heard other ones outside. Externally, you might use something differently in your company, right? So it's in the area of like New Relic, Datadog, Splunk. Name your like APM tool of choice that you normally deploy alongside your actual application itself, where it's able to grab the call stack of your code and basically stream or sample that your standard error started out and metrics and stuff like that out to some kind of external logger or metric system of some sort. So that's application insights now in so many words.
So I'm gonna close this out here. So we know the busy method here is potentially causing the issue. And why don't we check? I actually have the source code for this. And this is the example that Marcel has on his GitHub repo here. And you can,
Mhm.
of course, say, I mean, this was done on purpose to demonstrate, how this
Yeah.
tool would work. So you can say, of course, this is running there. It's just, gigantic loop.
Again, a cooking show, right? Like contrived scenario. Clearly, we made it a certain way, or in this case, Marcel has created an app that's basically just running this loop constantly, right? But it won't be this obvious to us, but at least this way we know for sure
I
because we
think
can.
it demonstrates, yeah, from an
Yeah.
education perspective, this is amazing because you can drill down and see, okay, here's what it is. But if I didn't have the source code, I could still make sense because you see, stay busy is what we saw on the flame graphs. So you
Yeah.
can definitely say, you know, this is what it is.
Yeah, perfect. Because the name of this actual function here in this particular class is called stay busy. And if we go back to the flame graph, right, that top like long plateau that you mentioned before, and I think it was red,
Yep.
in the SVG file, like it actually calls out that exact
Yeah. So if we open this up here again,
yeah.
that's it right here.
Yeah.
So you
So
would
the
say
source is the
class,
yeah, busy class method, stay busy. Perfect.
right? Which again, I think it's an interesting thing to we got into that conclusion without having source code, which I think it's amazing.
Yep.
So
Yep.
this right here. Now I want to call out one thing. Um, in what I'm showing you here, again, it's tailored to running AKS. And there is a second thing here that is done, which is we are turning on some debug profiling on the .NET uh, core itself, so we can actually get this perf information on Linux systems. When this was created, and you can see this in the deployment file, there is an environment variable that is called com plus underscore perf map enabled, and that's turned to 1. So it's a Boolean, you turn it to 1, and then you actually get the perf mapping. With this information and what I have out of the profiling, now I can make sense out of flame graphs. Otherwise, you'll be full of like unknowns because you don't have the symbols. So this is also important, Ray. I mean, it's I want to call this out. We'll put the link in there, but If you're profiling a .NET application, something like in Kubernetes, you need to turn this on to get the results that I'm showing you right now.
Basically, if I didn't turn this on, I wouldn't have seen like the class name and the method. It would just
You
say
would see a bunch
unknown.
of unknowns, yeah,
Yeah. Okay.
everywhere.
Right. Right. So
Conversely, if you have this on, but you don't have some other kernel headers, you would see the application, but then anything outside of the application, so kernel level, all those symbols will be lost, so you don't have a map, so
okay.
unknown everywhere.
Okay. So like if I see one or the other, right? Like if I figure, okay, this thing that is unknown, it looks like it should be at my application level. It's likely I didn't turn this on, right? I turn on the environment for variable for com plus. That's not turned on. If it's the other way around, I can actually see, class dot, or class and then the two colons for the denoting a method. I see that, but I don't see any of the other things. Like everything outside of that is unknown. Then I didn't turn on the proper headers for my Linux environment.
That's
And
right.
then
Yeah,
if I
that's
see
like
unknown throughout, I just didn't turn anything on.
so. If you see this,
Yeah.
and chances are we can probably optimize a little bit more because we're
Okay.
probably missing some. There's an opportunity here potentially for us to get these symbols,
Yeah.
right?
This is
Which we
kernel
don't.
space,
I believe it is.
yeah,
It's a little bit hard to say right now where this is coming from
right?
because you have all the way from the runtime and they might come back and forth. As you can see, like at the top, we had some of that.
Mm,
But I do have actually a second example here um, that will take us into an application that's a little bit more real, if you will. Like it's stuff that we see more often,
yeah. It's
which
not
is
just a
this.
oh, it's not a while loop that's just running. This is
No, so I still think that the get the application that we have the bad deployment that Marcel developed there, it's an
yeah,
amazing piece of it's part of your learning journey here. You definitely want to start with that.
yeah,
Make sense out of that, understand how that works, maybe modify the source code, recompile, drop it again.
mhm,
Now this is a little bit interesting because this is actually using a different application. It's also .NET, but you can see we have these little pillars here now, right? And they
yeah,
go all the way up actually to my monitor.
yeah. These crazy spikes and yeah,
And we can take in one of these, but if you're just looking into this and kind of applying the things we just discussed about, look at the plateaus and the plateaus that don't have anything on top of them. You wouldn't be looking only at this. Those are the areas that you probably want to inspect and see if you can optimize. So out of that, I think a good guess would be, I would start looking into this here first, right?
because there's a
And
lot of
potentially
plateauing
this.
here. There's not a lot of spikes. There's not a lot of small work
Yeah,
that's
they're like
actually
a
going.
big flat area, you
Yeah.
know. Um, Now in this specific application here, we have a semaphore, and there is a weight,
Mhm,
and about roughly 24% of the samples were spent under weight. That's potentially the problem here.
yeah.
This was an application that we had to profile. So this isn't like just a hello world. This is a little bit more complex.
Yeah.
You can also see that the application itself, this would give you some more insight. The application itself actually had Prometheus. We actually enabled Prometheus to harvest metrics out of this. So we were inspecting, getting metrics out of it. Again, with Prometheus, with Azure Monitor, with there was also App Insights, application insights from one of our tools that we use on this. And the flame graphs came in to help out with understanding where CPU was spent. So you can kind of, grasp some of that in out of this here. But the fact that you have about 24% in a weight, it raises some eyebrows. I mean, you're like probably an area that you want to spend time.
I think one thing as a tangent on this, I think we'll have to have a follow up video. Maybe we'll put it like as a link somewhere in the YouTube, top corner. We should actually get Lynn Oral, who's on our team too, to explain like the semaphore situation. Because Lynn, we are talking about .NET and C Sharp, but neither you and I should be writing uh, any of that. Lynn's the guy that we go to ask. So we'll have that in the session as to like where this might have gone off the rails and why a semaphore here, since we can
Yeah,
see
absolutely.
common language runtime semaphore. Like why is this problematic? Like,
And to your point, again, putting yourself in an SRE perspective here for a second, if you and I are doing this, and I'm not a .NET developer, so I'll put
Yeah.
that out there already. But I am able to inspect this, and then again, get somebody on an expert level like Lynn to come here and help us out understand, like, I'm looking into this. This doesn't look good to me from a performance perspective. Can you help me out understanding what's going on? So I think that having and that's normal in Kubernetes. You're not gonna have one person who knows all of this. It's too much things in place. At this level, what we're looking into stack calls, you're definitely calling the experts,
Oh,
right?
okay. One thing, since we're here in this realm, we kept on talking about .NET, C Sharp, but this again, like I know probably don't need to call it out, but I'm gonna call it anyways. This could be for any programming language. It could be for any
Totally.
program, right? Like this could
Oh
be,
yeah.
you know, Pascal. It could be, COBOL, whatever. Like this, and if it runs on Linux or if it runs on a system that we can actually profile using these BPF tools, we can basically take a look at this.
If it runs on Linux, we chances are we can get some data out of it for sure.
Okay,
It can
great.
be it could be Python, it could be Go, it could be Ruby. I mean, as long as we, and again, remember, we're also enabling the perf symbols. It could be Java as well, as long as we can get access to those symbols and we can make some sense. If we don't, we're going to get a lot of unknowns, but hopefully we have some information there, right? So
Awesome.
this is like an extra tool that you would want to use.
Yeah.
Um, so again, this is what it is, and maybe the one last thing I want to leave out. I mean, this is an SVG, right, Ray? I mean, you can zoom in, and you can also search. So if you were going to the top here and let's say, if I suspect for weight, it will highlight all of the words, right? So I can actually go in here and see why this comes. So all of this have like weight in their name. So it will highlight. Again, it makes life easy if you're suspecting about some of this stuff.
Mhm.
You can kind of do it that way, and you can also see like all of this here is actually kernel, the kernel stack. Like this is all kernel calls here. Um, if you
Now,
were,
now, how can I tell? Like, I'm I'm
how
a,
can
I'm
you
a
tell that this is
I'm a
actually
new,
kernel?
yeah. How do I know this is a kernel and not like an actual application?
Yeah, so right now the way this is done here, the colors don't really indicate whether or not this is a kernel. I know just because I've been looking into them long enough that I know that IP output or some of this is actually kernel. But if you are new to this and you're looking into it, you can actually see they're pretty different though. When you look into an application and how kernel symbols show up,
Hmm.
they're pretty different. The semantics are different between the
Yeah,
two of them.
yeah. Like I'm looking at like with the thing that you're pointing at here, this looks um like a method or like a full on like class signature in whatever
Yeah,
programming language I'm in, right?
it does. And
Yeah,
so that's kind of like how I would go about that too. I mean, of course, some of them it's pretty clear.
yeah,
But if you go up here and even these little pillars that we have, they can expand. And then in them, you probably see both side by side. You would see things like Prometheus. Again, this is something that we've added to the .NET source code. But then you can also see things like VFS, being read here, and that's on the Linux kernel. That's you're tapping now into the virtual file system, or you're calling out the TCP/IP stack and things like that. So you might have both. So if you suspect that what your application, so you're good with, there's nothing that I have to optimize. You suspect there's something in the it's outside as an operating system level. You can probably pick it up from here too. You could probably see what's going on. And Linux being open source, you can follow through that.
very cool.
So that was it. We'll leave the description here for where you can get this stuff, this information.
Okay,
I think, Ray, the one thing that you and I would ask here, this was of course a little bit longer than we initially thought, but I think it shows in a deep exercise. I'm a fan of the 5 minutes video, but I think in reality you want to cut out and have deeper dives, because this takes a lot of
yeah,
understanding of what we're trying to do.
yeah. So this will be like a core thing. We'll edit some of this up, maybe. Like, depends on how lazy I get. And then from this, we'll have like tranches of like additional information we'll dive into, like the semaphore thing with Lynn. Hopefully, we can get Lynn.
Sounds good. So hopefully this will help, other customers or SRE teams and developers.
Yeah, very cool. All right, man. Thanks, buddy.
Well, thank you. Till next time.